Alright, so hello everybody and welcome to this week's video. We'll be continuing with classical dynamics as before. Oh dear, what am I up to? It's because my microphone is too low and in the wrong place. There we go. We'll be continuing, as I said, with chapter 10, question number 6 today. Penultimate question. I am quite excited to finally finish this endless slog of magnetohydrodynamics. I mean, it's very slow. I could do it faster, but I enjoy having the regularity of one video per week. Anyway, let's get straight into the question. So 10.6 part A, or rather the prequel to the question, the setting up, says the effect of finite temperature on plasma can be described approximately by means of the correlationless Boltzmann or Vlasov equation. Let f of x, v, and t, where x is the position vector and v is the velocity vector, be the distribution function of the electrons of charge E and mass m in a one-component plasma. The Vlasov equation is that df dt is equivalent to the partial derivative of f dt plus v dot del xf plus a dot del vf is equal to 0, where del x and del v are the gradients with respect to coordinate or position vector x and velocity vector v, and vector a is the acceleration of an particle. For electrostatic oscillations of the plasma, the acceleration vector a is low e times big E over m, where big E is the macroscopic electric field, which satisfies this equation. Del dot E, or the divergence of E, is equal to 4 pi little e times the integral of f d cubed v minus n naught. If f naught v is some normalized equilibrium distribution of electrons, then it holds that n naught times the integral of f naught v d cubed v is equal to n naught. Yes. And part A asks us to show that the dispersion relation for small amplitude longitudinal plasma oscillations is k squared over omega p squared is equal to the integral of k dot del v f naught over k dot v minus omega d cubed v. Long question. It's actually fairly short, part A. Let's start with the 1D Vlasov equation as it's listed above, and also the second equation. I'll rewrite them in a slightly different form for clarity. df dt plus v del xf plus e over m dot del v is del vf is equal to 0, and also it holds that the divergence of E is equal to 4 pi little e times, let's do the integral first and then the bracket after, x v t yeah, that's nice. And we'll let the distribution function be perturbed around a uniform equilibrium, so f of x v t equal to n naught f naught v plus f1 x v t. And note also from our identity up here, this integral of f naught d cubed v is equal to 1. Now let's linearize this by dropping our second order term, which is over here because that's our accelerative one, and we should get that so df1 dt plus v dot x f1 plus e n naught m equals 0, and we can assume a plane wave solution for this, because it's an oscillation. You can kind of guess it there. So we'll take that minus I omega f1 plus I k dot v f1 is equal to minus e n naught over m e dot del v f naught. So we can rearrange for f1, which is factorizing and taking over to the other side. It holds that f1 is equal to, I'm going to do the denominator first, k dot v minus omega, obviously from here, over I e n naught times e dot del v f naught. Now we're looking at longitudinal oscillations. We are indeed looking at longitudinal small amplitude oscillations. The electric field will be parallel to the wave vector, so we can say here that E is equal to E k over k. And with that and that, we're going to substitute everything into our second equation here. And so it will hold that IKE is equal to 4 pi e times the integral of this over I, subbing in that, k over k del v f naught dqv, and we aim to rearrange now for k squared over omega squared. So we divide both sides by that. And we can substitute in then that omega p squared is equal to 4 pi n naught e squared over m, and leaving things inside the integral, IKE, so bring that back over, we get k squared equal to 4 pi n naught e squared over m times, then expanding this and obviously pulling out things, we get that k dot del v f naught over k dot v minus omega, taking out the m, d cubed v, and of course this is just omega p squared. I've just written it there, all over m. And so we can take that over to the other side just as easily. K squared over omega p squared is equal to the integral of k dot del v f naught k dot v minus omega d cubed v. Oh no. Very good. That is what holds in the question as well. Okay, part A is successful. As I always do, forgotten to write part A there. Now let's look at part B. So, question of part B. Assuming that the phase velocity of the wave is large compared to thermal velocities, we can show that the dispersion relation gives that omega squared over omega p squared is roughly 1 plus 2, and then the average k dot v over omega plus 3, the average k dot v squared over omega squared, etc., etc. So this is going to be a Taylor series expansion. I remember. So yeah, and then there's just a note that these these angled brackets mean averaged over the equilibrium distribution F naught V. And then we're asked to relate this result to that obtained in the text with the electronic fluid model, which is something in the book from earlier on in the chapter. Anyway, let's begin. So we'll start off with, well, first of all, if the phase velocity is much larger than the thermal velocity, that's omega over k is much greater than v, not omega. So k dot v over omega is going to be, if I actually put abs of that, is much less than 1, and that would be det. So 1 over k dot v, hello. It started lagging. I was like, what on earth is that? Minus omega. Let's continue. It is minus 1 over omega 1 minus k dot v over omega, not a little crab thing, to the minus 1. Again, this can be, well, now we can actually do the expansion. Minus 1 over omega is going to be, I'm going to pop it over here. 1 plus, I'm sorry if this gets so small, k dot v over omega plus k dot v squared over omega squared plus k. I did not need that much space. Better be safe than sorry. A omega cubed plus dot dot dot. Nice. Now we will sub this into the dispersion relation from earlier. So we get that k squared over omega p squared minus 1 over omega times the integral. I'm just going to check what the integral was. Yep, cool. So that makes it k del v f naught, that's just the same as before, in brackets, times that. I've already put that in, haven't I? 1 plus k dot v over omega plus k dot v squared over omega squared. I'm not going to write the rest in. D cubed v. And we can evaluate this integral term by term using integration by parts on this. So for some nth order term, also we can assume that, oh, it's doing it again. Can we not have all the technical issues, please, now? What is wrong with you? So unplug and replug. Boop. Hello. Right, there we go. Hopefully that's fixed now. F naught tends to 0 and V tends to infinity, plus or minus infinity, as we go on. We can take for the nth order term that k dot del v f naught k dot v to the n d cubed v is equal to minus, not a zeta, minus the integral of f naught del v dot k dot v to the n. That seems right because, yeah. Now we can use chain rule on this, or rather reverse chain rule. So del dot k times k dot v to the n is k dot del v times k dot v to the n, which is k dot n times k dot v to the n minus 1k, which is nk squared k dot v to the n minus 1. That seems right. So this then is just minus nk squared. There's going to be a lot of trouble with me trying to draw those. K dot v to the n minus 1. This is just equilibrium distribution f naught. We can do a couple of terms of this. So n equals 0. That's just going to be 0. N equals 1 is going to be minus k squared over omega 1, which is minus k squared over omega. N equals 2 is going to be minus 2k squared over omega squared. And then that'll just be k dot v. And n equals 3. I think this should be all we need, minus 3k squared over omega cubed k dot v squared, squared in the bracket. Yeah, that should be along the lines of what being asked here to show. So if we just divide both sides by k squared and then divide by k squared, multiply by omega squared, omega p squared, I think on both sides. In fact, I might just write out the whole thing and then it'll be easier. So k squared over omega p squared is equal to minus 1 over omega 0 minus k squared over omega minus 2k squared over omega squared k dot v minus 3k squared over 2 k dot v squared minus dot dot dot. And now we can, this is what I was trying to say, but it was in my head, so it probably wasn't being said very clearly. We can pop k from both sides, or from everywhere, and then multiply by omega, which will get rid of that and put that there. That's not 2, I'm not sure where I got that from. Regardless, this gives us that omega squared over omega p squared. What was the exact notation they used? Was it a squiggle and then a line? Squiggle on 2 lines, squiggle on 1 line. Alright. Says the physician to the mathematician. Physician, physicist. Oh dear. K dot V over omega plus 3 K dot V squared over omega squared plus dot dot dot. Let's pop it in a box. And that is what is being asked of us for part B. Now, it asks for the relation to the fluid model. So what I have in my notes, in a thermalized plasma at rest, actually, what do we got to stay here? I think we can go up, because, no, there's not much useful stuff. I guess we have all the equations there. So in a thermalized plasma at rest, drift velocity is 0, so that means that this term, I need a different pen. This k dot v is equal to 0. I'm not going to keep those rounds because I don't want it to get in the way. And that means that k squared, this k squared times the average v squared where it's parallel, is k squared times Boltzmann constant times temperature over m. So the dispersion relation truncates more. Omega squared is roughly omega p squared plus 3k squared kBt over m. And this reproduces the Bohm-Gross, I don't know how to pronounce their names, dispersion relation, which is what it's getting on about here. For a warm fluid, it shows that the adiabatic coefficient gamma for the 1D compression of electron waves is naturally 3 due to the 1D constraints of the longitudinal wave vector. That's pretty cool. Nice marriage between some thermal physics and some electrodynamics. Part C is another talky one, so I'm sorry about that. Part C asks, what is the meaning of the singularity in the dispersion relation when k dot v equals omega? So when k dot v equals omega, then obviously all of these terms will simplify down to be 1 plus 2 plus 3, etc., etc. So this corresponds, or actually you can also say when the v is in phase, or it's omega over k. This corresponds to particles moving at exactly, when particles are moving at exactly the phase velocity of the wave, they experience this static, non-oscillating DC electric, of course non-oscillating, they experience a DC electric field in their rest frame, and this sort of lets this secular continuous energy exchange between the wave and the resonant particles. It completely breaks the adiabatic fluid approximation from above, or from before. Depending on the slope of the distribution function at v phase, so df to t, which is the whole important thing from this, the physical singularity leads to either collisionless wave attenuation or wave growth. And this whole thing is called Landau resonance. Goodness me, Landau resonance. I said it again. Landau resonance. So when you have that, depending on the slope of the function, the distribution function, the collisionless attenuation is called Landau damping, and the growth is just unstable equilibrium. But yeah, I thought that's also quite interesting thing it gets on about. I don't know how much maths there is to do there, but it's certainly a heavy concept to get your head around. But anyway, that does bring us to the end of this video. I hope that you're not getting as sick of these as I am. But there is one left, and I'm going to go and do it now, and then it will be ready for next week. And then after that, I'm sure we'll move on to some exciting endeavours. I've had 7 weeks to plan things to do, and I haven't even thought of a single one, so I'm sure I'll find something. I thought of a few things. But yeah, anyway, I hope you found this interesting, and I'll see you next week. Goodbye.